Chapter 17, Part 1, we are going to talk about Bernoulli trials and the geometric model. Before we get into these two new ideas, I want to start with an introduction question. So, Jerrio is out on the soccer field practicing his shooting. He tells his friends that the probability of successfully hitting the crossbar is 20%. Assume that each shot is independent. For my non-soccer player friends out there, the soccer goal looks something like this. Okay, the crossbar is this top bar. So Jerrio's trying to hit this top bar with the soccer ball. After the first 10 shots, Jerrio wants to do 10 more, but his coach is getting annoyed and tells him that he must stop once he hits the crossbar. So part 1, we want to find the probability that he hits the crossbar on the very first try. So this would just be the first try. The probability of him hitting it is just 20, so my answer would be 0.2 or 0.20. Don't really have any work there. Number 2 says find the probability that he fails on the first try and hits it on the second try. So in the first try he does not make it. So if the chances of him making it is 20, we could use our complement rule to find the chance that he doesn't make it. 100 minus 20% would give me an 80% chance that he doesn't make it. So if he fails on the first try, that's going to be 0.8. I'm going to multiply that because this is an AND problem, and AND problems are always multiplying. So the chances he hits it on the second try is 0.2. 0.8 times 0.2 gives me 0.16. And we're just going to keep going here. Part 3, or number 3, says find the probability that he fails on the first 2 attempts and hits it on the third try. So we're failing once, so that's 0.8, times another 0.8, and then hits it on the third try, so now I'm at 0.2. You could also write this as 0.8 to the second power, because those first 2 times he's missing, and then multiply by the 0.2. Doesn't matter how you plug it into your calculator. 0.8 times 0.8 times 0.2 gives me 0.128. Right, number 4, he's failing the first 3 times and then finally hits it on the 4th try. So I'm going to do 0.8 to the third power and then times 0.2. We get 0.1024. Now technically what we've been doing here is working with a random variable. So if we say that x is the number of shots that it takes for Jerrio to hit the crossbar, we could make a probability distribution chart. Now we are using a probability distribution chart because this is a discrete random variable. There's no way that it can take him 1.5 tries or 1.2 tries. It's just whole numbers here. So the probability that he makes it on the first was 0.2. Probability of making it on the second was 0.16. Then we had 0.128, 0.1024. Okay, we can go ahead and find the 5th one. If he's making it on the 5th, that means he misses the first 4. So we would have 0.8 to the 4th power times 0.2. Giving us 0.0819. I'm just going to round to 4 after that decimal. 6 shots would be 0.8 to the 5th. He's missing the first 5 and then making the last one. So I'm just going to change this exponent to a 5, and we get 0.655. Now with these probability distribution charts, we know that the probabilities should add up to 1. So real quick, I'm going to go ahead and type these in. Just 0.2 plus 0.16 plus, and just adding up all of these probabilities. And I only get 0.7378. Now the reason that this is true is because technically this random variable is going to continue on and on and on. it could take Jerrio 20 shots to hit that crossbar. There's no really stopping point here. So in order for these probabilities to add up to 1, I would have to continue my probability distribution chart until I get at least close to 1. We're going to stop there so we can look at kind of how to find these probabilities here in a little bit of an easier way. If you recall back to chapter 6, we looked at the normal model, which was a special probability model. We also used that normal model when we were looking at continuous random variables. In chapter 16, we constructed probability models for many discrete random variables. So we looked at different card games or carnival games and created those probability distribution models. In this chapter, we're going to see 2 more special probability models. And the 2 models that we're going to look at are called Bernoulli trials. Bernoulli trials have the following characteristics. They need to have 2 outcomes and only 2 outcomes. There should be a fixed probability of success, meaning that that probability of success shouldn't change each time. And each trial should be independent. Okay, so a couple examples here. You could flip a coin. Your 2 options for flipping a coin are heads or tails. You could roll a dice and want to get an odd number. Your 2 options then would be getting an odd or an even. Taking free throws shots in basketball, you either make the shot or you miss the shot. Guessing on a multiple choice question, you could either get the question right or get the question wrong. Another example is having Mrs. Soto as your Algebra 2 teacher. Could we make this have just 2 events? Now, if you think about it, when I think about this question straight away, to me, I think, well, no, there's more than 2 outcomes. I could have Mrs. Soto, or I could have Miss Wenzitz, or I could have Miss Mollahan. There's tons of different Algebra 2 teachers. But if you can make it so that there are 2 outcomes, then you can do that for this Bernoulli trial. So I could have this as just a yes or no question. Either yes, you have Mrs. Soto, or no, you do not. Okay, go ahead and take a minute. I want you to try A through D. You're just determining if these scenarios are Bernoulli trials or not. Okay, part A said find the probability that the top card on the deck is an ace. You could make this a Bernoulli trial by saying either it's an ace or it's not an ace. B said recording the distribution of eye colors. This is definitely not, because you are recording the distribution of the different eye colors. So you're going to have blue, green, brown, hazel, all the different eye colors listed out. Part C says determine if your newborn child is a girl. That would be yes, because your options are girl or boy. And part D said rolling a dice and recording each value. This would be no. Again, there are not 2 outcomes. You're recording each value there, so you can have anything from 1 through 6. Now, there are 2 types of Bernoulli trials. The first type that we're going to look at is called a geometric model. So we're going to start with looking at kind of some specifics here and notations for that geometric model. Okay, with this geometric model, we will use this when we want to find out how long it will take to achieve the first success. The big idea here is that we are looking for the first success. So if you think back to that example we started with Jerrio, we were looking for how long it would take him until he hit the crossbar. That would be our first success. Now, when we're working with geometric models, we are going to use this little acronym here, just GOM. Sometimes we just put geo. You might put geomet. That would be fine. Any of those notations there will tell us we're looking at a geometric model. Now, with geometric models, we are going to have P and Q. P is the probability of success, and Q is the probability of failure. Typically, they will only tell you the probability of success. You can find the probability of the failure by just doing 1 minus P. So Jerio had a 20% chance of hitting that crossbar. We found his chances of failure by doing 1 minus the 0.2. X is the random variable that we're looking for. This is the number of trials until the first success. So how many times does Jerio have to shoot that soccer ball until he hits the crossbar? Now, notation-wise, what we're doing here is if we're finding the chances that the number of trials is equal to a certain number, we're going to take the chances of failure, so that's our Q. Exponent-wise, I'm going to do the number of trials minus 1, and then I'm going to multiply by the chances of success. And I think that looks kind of crazy, but we actually used this back on page 35. When I was looking for the chance that he would hit it on the 5th one, we had an exponent of 4, which was 1 less, so that's where that minus 1 is coming from. This was our failure, so our Q, and this was P. Okay, sometimes questions will ask you to find the expected value. How many trials do you expect to happen until you reach a success? To find this, you're going to take 1 and divide by the probability of success. So just 1 divided by P. Standard deviation is a little bit trickier. You're going to take the square root of the chance of failure, so Q, divided by the probability of success squared. Both of these formulas here will be given to you on the test. You'll have a formula sheet, and these are both given to you, which is very nice to have. Let's go ahead and look at example 1. Example 1 says that Maddie watches a lot of Criminal Minds, which I totally understand. Criminal Minds is one of my favorite shows, so I totally understand that you'd be watching a lot of it. Maddie determines that when she watches TV, she watches Criminal Minds 91% of the time. Okay, we want to find how many times should you expect to ask Maddie what she's watching before she says something other than Criminal Minds. So this is a Bernoulli trial. There are 2 outcomes. There's either she's watching Criminal Minds, which I'm just going to call CM, or she's not watching that. Okay, we want to find how many times you expect to ask her. So I'm looking for expected value here. And what we want to find is she says something other than Criminal Minds. So I'm looking for the chances that she's not watching Criminal Minds. So what I'm going to do is take 1 and divide by the chance that she is not watching Criminal Minds, which would be 1 minus this 0.91, which gives me 0.09. So I'm going to put that 0.09 in my denominator. Again, I'm 1 divide by the chance that she's not watching Criminal Minds, she's watching something else. And I get 11.11, and this is representing times that you ask her. Okay, again, this is an expected value, so it's just an average, which is why it's not completely making sense in terms of the real world. I can't ask Maddie 0.11 times, but roughly, as I ask her more and more and more, around, it's going to take me 11 times until she says she's watching something other than Criminal Minds. Okay, part B says, what's the probability that the 4th time you ask Maddie if she's watching Criminal Minds is the first time she says no? Okay, what's happening here is that the 4th time I ask her is going to be the first time I get a success. So I'm going to think about this kind of like we did with the Jerio problem in the beginning. If the 4th time is the first time she says no, that means that she's going to say yes, she's watching Criminal Minds for the first 3 times. So I need to do the probability of Criminal Minds for 3 times, and then we'll multiply that by the probability of not Criminal Minds for 1 time. So the chances she's watching Criminal Minds was the 0.91, raising that to the 3rd power, representing those first 3 times. Not Criminal Minds is only 9%. So I'm going to do 0.91 to the 3rd times 0.09. So about a 6% chance that the 4th time you ask her is going to be the first time that she says she's watching something other than Criminal Minds. Okay, we're going to stop this video here and look at some more examples and some calculator tricks in the next video.